All right. So let us understand the measures of dispersion. The underlying logic is clear is what I'm assuming. Now let me get into the math part of this. Say, let me choose a different color. Okay. Say I have, oh, sorry. Yeah. Say you have retail stores in India, US, and UK. You know that the first question is on an average, what are our profits, etc. The second question would be from any management person on, is the variation in the profits across these locations the same, or is there a huge variation? Yeah, that would be your obvious second question. Hence, measures of dispersion is also called as second moment business decision. Second moment business decision. All right. Now let us understand the second moment business decision using the Excel sheet. Yep. Here I've already written these examples. Let us understand. I've written here that this is second moment business decision because this is the second question which any management person would ask. I have a data set as an example. Say I'm measuring the weights of the kids, right? Weight of the first kid is 10 kgs. Weight of the second kid is 20 kgs. And the weight of the third kid is 30 kgs. The formula to calculate variance is as follows. Sigma I equal to 1 until n xi minus mu whole square, and you divide it by n. Here I have three numbers, so I'll write this as sigma I equal to 1 until 3 xi minus mu whole square, and instead of n I'm going to replace it by 3 because we have 3 data points. If you were to expand this, if I substitute I equal to 1, it will be x1 minus mu whole square plus I equal to 2 x2 minus mu whole square plus I equal to 3. So it will be x3 minus mu whole square, you divide it by 3. Alright, so this is the formula. Now let me try to erase all these values and do it right from the scratch. I'll remove all these values. Just give me a moment. Yep. So I've removed all these values. Okay. So the weight of first person is 10 kgs, second person is 20 kgs, and the third person is 30 kgs here. In the formula here, we need to calculate mu. What is mu? Mu is nothing but mean of the population. All right. So if you calculate the mean here, which is average of all these three values, it happens to be 20 kgs. This is the first step. Now let us calculate xi minus mu. So go here, it is xi minus mu. Xi, that is x1 here, x1 minus mu is 10 minus, this is your mu. So it is minus 10 kgs. x2 minus mu is the next value. So x2 is here minus mu is here. It is kgs. Then we have x3 minus mu. Here we have x3 minus mu. And we have kgs, right? Now if I do a summation of these values as is without doing a square, I will get 0. which is wrong. There is some variation, right? There is some variation in the weights. How can you say that the variation is zero? We cannot say so. Hence, to get rid of that problem in this formula, mathematicians have told that we need to take a square of this. So it's x1 minus mu whole square. x1 minus mu is minus 10. Minus 10 whole square, it will become positive. So it's 100 kgs square. Units also get squared. And then x2 minus mu whole square, which is 0 square, which is 0. Units get squared to kg square. And then you have x3 minus mu whole square. So it is x3 minus mu is 10. 10 square is 100. You get kg square once again. Now, we need to take a summation of all these three values. Yeah, if you take summation of all these three values, you get 200 units is important, kgs square. Now, if you want to calculate variance, it is nothing but summation of all these three values divided by 3. So it will be 200 by 3, and the units will still remain as kgs square. So it is 66.6666 something kg square. Does kg square make sense? If I ask you all on what is the variation of the weights of the students of this class, and if you say it is 66 kgs square, it doesn't make sense. If I ask you on what is the variation in the salaries of the employees of your department, and if you say it is $1,000 square, it does not make sense, right? Hence, statisticians have come to our rescue yet again by coming up with a new measure called as standard deviation. And standard deviation is nothing but square root of variance. You have the variance here. If you simply take a square root of that, you get standard deviation. So let me take a square root. This is a function for square root in Excel. Of that value happens to be 8.16, and if you take the square root of kgs square, you'll get kgs. This is the only difference between standard deviation and variance. Since variance has a problem of units getting squared, we take the square root of that to get standard deviation. There is yet another measure called as range. Range is given using the formula maximum value minus minimum value. Since there are three numbers, it would be relatively easy for you all to identify what is the maximum value here, right? Maximum value is 30. But what if I give you millions of records and ask you to find out the minimum value or maximum value? You need to resort to functions. So here max is a function. You just need to select these three. It would say that 30 is the maximum value and min would give you the minimum value. Now range is nothing but the minimum value minus maximum value, which happens to be 20 kgs. Now, there is a small anecdote here. Say you want to cross a river and you have to cross it by walking. And you ask a person who is on the ship, on what is the depth of the river? He says it is 4 feet on an average. The depth of this river is 4 feet on an average. And your height is 6 feet. Would you cross the river? You would most often than not, right? You don't know swimming. So it might turn out to be that it's your career-ending move. So you'll not do that, right? Hence, in this kind of a scenario, you might want to ask the range. What is the maximum depth of the river and what is the minimum depth? Based on that, you can take a strong decision on whether you want to cross the river or not. All right. The one key difference between population and sample formulae pertaining to variance and standard deviation is that here you have n, here you have n and here you have n minus 1. There is a reason for that. When you calculate variance for the population, you will get slightly smaller value. But when you calculate the variance for a sample, you tend to get a slightly higher value. Let us try to see whether that holds true or not. We can create a few data points here. Let me create those. 10, 20, 40, 60, 70, 80. Some numbers I'm randomly generating. Yeah. Now if I calculate the variance for this, I get 655.55, right? However, if I take a sample, so I'm randomly taking a sample, and now if I try to calculate the variance for the sample, look at that. I get 233.33, right? And if I calculate variance for population here, I get 155.55. So please notice, let me explain this. So this is your population variance, and the formula is summation of I equal to 1 until n xi minus mu whole square divided by n. This value is your, let me see, yeah, sample. This value is your sample variance. I'll come to the formula of that. This is your population variance once again. What happens here is, in this scenario, population variance will be slightly higher, but when you calculate your population variance for a sample, or when you calculate the variance for sample using the same formula here, I've employed the same formula here. You see that there is a huge difference. For population variance and for sample variance, if I use the same formula, there's a huge difference. However, when it comes to the sample variance, the difference between these two has slightly reduced. Difference between these two has slightly reduced as opposed to difference between these two, right? Because the formula here is as follows: sigma I equal to 1 until n xi minus x bar whole square divided by n minus 1. This versus this, right? Just think on these lines. If I divide 10 by 2 or 20 by 2, I would get 10, right? Here, if I reduce the denominator, what would happen? Or let me give you this example. Forget about this. 20 by 4 is equal to 5. Yeah? Now, what will happen if I reduce the denominator? Here I'm reducing the denominator. I'm subtracting the number of data points minus 1. What do you think will happen? If I reduce this, say I'm reducing the denominator from 4 to 2, what will happen to the actual value? It will increase. Right? So your sample variance would at least be slightly closer to your population variance. But if you use the same formula that you're using for population variance and calculate sample variance, it will actually go down further. And this is the reason why you use n minus 1 here. That is the reason why there is n minus 1 in the denominator.